dark matter.
Ooh, dark matter.
It's going to be a good one.
I'm excited.
We've got a whole stack of scientific articles and explanations here
Excellent.
that we're going to be taking a look at and
Awesome.
trying to break down for everybody.
Love it.
So
Yeah.
basically, we're talking about the invisible stuff that makes up most of the universe.
Yeah, most of the mass of the universe. Invisible.
Right.
Crazy, right?
I mean, how do we even know that it's there?
Well, that's a great question.
So we're going to
That's what we're going to talk about.
be exploring what dark matter is,
Okay.
how we even know it exists,
Yeah.
and what it means for, well, everything.
Yeah, the whole universe.
So to kick things off,
Okay.
one of the biggest pieces of evidence for dark matter is that galaxies are spinning way faster than they should,
Right.
based on what we can see.
Much faster.
Like there's some invisible hand
It's why.
just kind of holding them together.
Yeah. Exactly. So think about it. You'd expect stars farther from the center of a galaxy to orbit slower,
Okay, yeah, that makes sense.
just like planets farther from the sun, right?
Right.
Take longer to go around.
Makes sense.
But astronomers have observed that stars on the outskirts of galaxies are zipping around way faster
Really?
than they should based on the visible matter that we can see.
So there's something else there
There's got to be something else there.
that we're not seeing.
Exactly. It's as if something massive
Okay.
but invisible
Yeah.
is holding them in their orbits.
Wow.
Like a cosmic game of tug of war, and the invisible team is winning.
That's crazy. Okay, so we've got these like speedy stars
Yeah.
as like our first clue. What other evidence do we have that points to this mysterious dark matter?
So there's this really cool thing called gravitational lensing.
Okay.
Okay, imagine you're looking at a distant galaxy through like a super powerful telescope, right? If there's a massive object, like a cluster of galaxies, between you and that distant galaxy, the gravity of that cluster bends the light coming from the distant galaxy.
So it's like distorting it.
Yeah, it distorts.
Oh,
It acts like a cosmic magnifying glass. So it distorts the image of the galaxy behind it.
So we can actually see the distortion
You got it.
caused by something that we can't even see.
Yes.
That's mind-boggling.
It is mind-boggling.
Yeah.
But here's the thing. Here's the kicker.
Okay.
When we measure the amount of distortion,
Yeah.
it tells us there's way more mass in that cluster than we can account for,
Oh, wow.
with just the visible stars and gas.
That's crazy.
It's like seeing the footprints of a ghost.
Wow.
Right.
That's a really good analogy.
Thanks.
So we've got the
Yeah.
speeding stars.
Yes.
We've got this cosmic lensing effect, both hinting at this massive something
Right.
lurking in the shadows.
Yeah.
Anything else?
Okay, so we also have the cosmic microwave background radiation.
What is that?
So basically, it's like the afterglow of the Big Bang.
Oh, wow.
Right? It's this really faint signal that like permeates the entire universe.
Sure.
And it gives us a snapshot
Okay.
of the universe when it was just a baby. Like only about 380,000 years old.
So we're going way back
Way, way back.
to the beginning.
To the beginning.
How does this baby picture of the universe
Yeah.
relate to dark matter?
Okay, so imprinted within this radiation are these tiny fluctuations in temperature. Okay, and they act like a cosmic fingerprint,
Okay.
revealing the distribution of matter and energy in the early universe.
Sticker.
And guess what? The pattern of these fluctuations
Yeah.
strongly suggests that dark matter was a major player, even back then.
Wow.
Yeah.
So from the way galaxies spin
Yep.
to how light bends around massive objects, all the way back to the afterglow of the Big Bang,
Right.
it's all pointing
It all points.
to this mysterious dark matter.
It's pretty wild.
Okay, I am officially intrigued.
Good.
But if we can't see it,
Yeah.
interact with it directly,
Yeah.
how do we know
How do we know?
what it's made of?
That, my friend, is the million-dollar question.
Yeah.
And believe me,
Okay.
scientists have come up with some pretty wild ideas.
Okay.
So the standard model of particle physics, which like describes all the known particles and forces, it doesn't account for dark matter.
So it's got to be something totally new.
Totally new. It's got to be something completely new.
All right, I'm ready.
Okay.
Spill the beans. What are some of the leading contenders
Okay.
in this like cosmic lineup?
All right. So one of the most popular candidates is something called a WIMP,
A whim.
which stands for Weakly Interacting Massive Particle.
Okay.
Yeah. So WIMPs are these hypothetical particles that are thought to be heavy,
Okay.
and they interact very weakly with regular matter,
Okay.
just like their name suggests.
So they're like what? Like cosmic ninjas?
Yeah, like cosmic dungeons.
Slipping through the universe unnoticed.
Totally. And because they interact so weakly, they're incredibly difficult to detect.
Okay.
We've been searching for them for decades.
Really?
But so far, nothing.
Wow.
They remained elusive.
So that's a tough one.
It is a tough one.
Are there any other candidates?
Okay, so another possibility is the axion.
The axia.
Which is a hypothetical particle that's
Right.
much lighter than a WIMP.
Okay.
Now, axions were originally proposed to solve a different problem in particle physics.
Oh, really?
But they also happen to have properties that
Yeah.
make them a viable candidate for dark matter.
So they're like overachievers.
Yeah, they're like the overachiever.
Solving multiple mysteries at once.
Exactly. They're multi-talented.
I like it.
Yeah.
Okay, what else do we have?
All right, then we have sterile neutrinos,
Sterile neutrinos.
which are these hypothetical cousins of the regular neutrinos we already know about.
Okay.
Now, regular neutrinos are incredibly light,
Okay.
and they barely interact with matter. But sterile neutrinos, they're thought to be even more elusive.
Oh, wow.
Like, they interact so weakly
Yeah.
that they could pass through light years of lead without a single collision.
Wow.
Yeah.
Okay, so we've got these WIMPs, axions, and sterile neutrinos all vying for this title of dark matter.
It's like a cosmic mystery novel, right?
It is.
Yeah. And we're trying to figure out who done it.
Exactly. But how
Yeah.
are scientists actually trying to catch these cosmic ghosts?
Right.
We can't just, like, set a dark matter net
No.
out in space,
You
right?
can't just set a trap,
Yeah.
unfortunately. Although that would be amazing.
That would be awesome.
Right.
Yeah.
But there are some
Oh, they do?
incredibly clever
Okay.
methods being used
Okay.
to hunt for these elusive particles.
All right.
So one approach is direct detection,
Okay.
where scientists build these ultra-sensitive detectors deep underground, shielded from all the other particles that are constantly, like, bombarding the Earth.
Okay.
So the idea is, if a dark matter particle happens to collide with an atom in the detector,
Okay.
it would create a tiny signal
Okay.
that we could measure.
So it's like searching for a needle in a haystack.
Pretty much, yeah.
Wow.
Yeah.
What about indirect detection?
Okay, so for indirect detection,
Yeah.
scientists look for the fallout
Okay.
from dark matter interactions in space.
Okay.
For example,
Okay.
if two dark matter particles collide and annihilate each other,
Mm-hmm.
they might produce gamma rays,
Okay.
which we can detect with telescopes.
Okay.
So it's like looking for the smoke to find the fire.
Gotcha.
Yeah.
So we're looking
If
for
you're looking for any sign,
like any little telltale sign
any little hint. Yeah.
that these
Yeah.
elusive particles
Right.
have left their mark
Exactly.
on the universe.
Uh-huh.
Okay, so what about creating dark matter ourselves?
Okay, so that's where particle colliders, like the Large Hadron Collider, come in.
Huge.
Yeah, by smashing particles together at incredible speeds.
Yeah.
Scientists hope to create new particles,
Okay.
including, possibly, dark matter particles.
Wow. So we've got these theoretical particles. That could be the key to understanding dark matter.
Yeah.
And we're using all these amazing methods
Uh-huh.
to try and track them down.
Exactly.
This
This
is
is pretty incredible.
All incredibly exciting.
It is. It is.
But what does all of this mean for the universe as a whole?
Well, that's a great question.
Yeah.
And that's what we're going to talk about next.
All right, let's do it.
Okay.
So we've been talking about these elusive dark matter particles and how scientists are trying to, detect them.
Right.
But I'm kind of curious, like, what does dark matter actually do
Yeah.
in the universe?
It's a great question.
Is it just like out there
Yeah.
floating around?
Yeah.
Or is it actually like
Right.
doing something?
Right. So it's definitely not just sitting around.
Okay.
Remember how we talked about how dark matter outweighs regular matter by about 5 to 1?
Yeah, yeah.
That means that its gravity has a huge influence on how the universe is structured
Oh, wow.
and how it evolves.
Okay.
In fact, without dark matter, we might not even be here to talk about it.
Okay, now that's a big statement.
It is a big step, but it's true.
How could dark matter be responsible for our very existence?
Okay, so let's rewind all the way back to the early universe.
Okay.
Just after the Big Bang.
Okay.
Everything was incredibly hot and dense.
Yeah.
But as the universe expanded and cooled,
Okay.
tiny fluctuations in density started to appear.
Okay.
These were like little seeds of matter.
Okay, so picture a smooth cosmic soup.
Yeah, like a smooth cosmic soup.
And then also little clumps
Little clumps start forming.
that are forming here and there.
Now, regular matter was still too energetic to really clump together under its own gravity. It was like trying to build a sandcastle with sand that's constantly being blown around by the wind.
Right, yeah.
You can't really do it.
So that's where the dark matter comes in.
That's exactly where dark matter comes in.
Okay.
Because dark matter only interacts through gravity.
Uh-huh.
It wasn't affected by all the heat and radiation flying around in the early universe.
Oh.
It could start clumping together under its own gravity, forming a kind of cosmic scaffolding.
Okay, so I'm picturing this scaffolding.
Yeah.
Made of dark matter.
Yeah, scaffolding of dark matter.
And then what happens?
So as this scaffolding of dark matter grew denser, its gravity started pulling in the regular matter.
Okay.
Helping it to clump together as well.
Okay.
Eventually, these clumps became massive enough to collapse under their own gravity, forming the first stars and galaxies.
So dark matter acted like
a
cosmic shepherd gathering
the sheep
of regular matter.
And guiding them into these giant structures that we call galaxies.
Wow, that's a really good analogy.
I like that one.
Yeah, so without dark matter acting as this like gravitational glue.
Yeah, it's like the glue. Galaxies might have never formed.
Yeah, it's pretty amazing.
And the universe would be a very different place.
Very different.
Much less interesting.
Yeah, definitely less interesting.
Wow. I never really thought about it that way.
Yeah, it's pretty mind-blowing.
But wait, if dark matter is so good at pulling things together, why isn't the universe collapsing?
That's a great question.
In on itself.
Yeah, and it leads us to another fascinating aspect of dark matter's influence.
Yeah.
Its role in the universe's expansion.
Okay.
Yeah.
I thought the expansion of the universe was all driven by dark energy.
You're absolutely right.
Dark energy is the dominant force.
Force that's pulling everything apart.
Yeah, behind the accelerating expansion we observe today.
Yeah.
But dark matter plays a crucial role, too. Its gravity actually counteracts the expansion to some extent.
Oh, really?
In slowing it down.
Okay.
Yeah.
So it's like a cosmic tug of war.
Exactly.
Between dark matter pulling things together and dark energy
pushing them apart. Exactly. And the outcome of this cosmic tug of war depends on the relative amounts of dark matter and dark energy in the universe.
Oh.
It's a delicate balance.
Yeah.
And scientists are still trying to determine which side will ultimately win.
So if dark matter wins, what happens? Does the universe just collapse like a deflating balloon?
That's one possibility.
Okay.
If the density of dark matter is high enough, its gravity could eventually overcome the expansion, leading to what's called the Big Crunch.
The Big Crunch.
The Big Crunch.
Oh.
In this scenario, the universe would contract.
Okay.
Galaxies would collide.
And everything would
eventually collapse back into an incredibly hot, dense singularity, much like the state from which it originated in the Big Bang.
Wow, that's a pretty dramatic ending.
It is a dramatic ending.
Like a cosmic reset button?
Yeah, a cosmic reset button.
Wow.
But what if dark energy wins the tug of war?
Yeah, what happens then?
If dark energy continues to dominate,
the
universe will keep expanding forever at an accelerating rate.
Oh, wow.
And this leads to a very different end known as the Big Freeze.
The Big Freeze.
The Big Freeze, yeah.
Okay.
In this scenario, galaxies will become increasingly isolated from one another.
Okay.
Stars will eventually burn out.
And the universe will become a cold, dark, and empty place. So it's either a fiery collapse or a slow fade into darkness.
Yeah, those are the two main options as we understand them right now.
That's intense.
It is pretty intense.
To think that something we can't even see could have such a profound impact on the fate of the entire universe.
It really makes you realize that the universe is full of surprises.
Yeah.
And there's still so much we don't know.
And it's kind of inspiring.
It is inspiring.
To think that, we humans, with our very limited senses and our
short lifespans
are able to even probe these cosmic mysteries and uncover these hidden workings of the universe.
Absolutely. And who knows what other amazing discoveries await us as we continue to explore the world of dark matter.
I'm curious to kind of explore the potential implications of dark matter for us here on Earth.
Yeah.
Could unlocking its secrets lead to new technologies?
Yeah.
Or even change our understanding of physics?
That's a really great question.
We've talked about how dark matter shapes galaxies and how it affects the universe's destiny.
Right.
But I'm wondering, could understanding of this invisible stuff have any implications for us here on Earth?
It's really hard to predict the future, but the pursuit of knowledge often leads to unexpected breakthroughs.
Yeah.
Think about it. The discovery of electricity completely revolutionized our world.
Yeah, for sure.
Led to everything from light bulbs to smartphones.
Yeah, it's crazy to think about.
I know. Who could have imagined such transformations back when electricity was just this scientific curiosity?
Right.
Right.
So you're saying unlocking the secrets of dark matter could have similar ripple effects, even if we can't really see them now.
Exactly.
Okay.
So let's start with the most direct implication, a potential revolution in physics.
Okay.
Right now, our understanding of the universe is based on the standard model of particle physics,
Right.
which describes all the known particles and forces.
Right.
But the standard model doesn't account for dark matter.
So finding out what dark matter is made of could, like, completely change the standard model.
It would be a major paradigm shift.
Wow.
You know, if dark matter is made of these exotic particles we've been talking about, like WIMPs or axions, it means there's a whole sector of particle physics that we've been completely blind to.
It's like discovering a hidden continent.
Yes. It's like discovering a hidden continent on a map of the world.
The hidden continent of particles and forces.
Exactly.
That's wild. But would this new physics just be theoretical, or could it lead to practical applications?
It's impossible to say for sure.
Yeah.
But history has shown that advances in fundamental physics often lead to technological innovations.
That's true.
Like, think about how Einstein's theory of relativity,
Yeah.
which seemed like a really abstract concept at the time,
Yeah.
eventually led to GPS technology
That's true.
that we use every day.
Wow. Okay.
Right.
So maybe we'll have dark matter-powered cars someday.
Well,
Or
right.
devices that can manipulate gravity.
I mean, it's possible.
That would be pretty wild.
It would be amazing.
Okay, so the point is,
The point is that understanding dark matter could open up entirely new avenues for scientific exploration and technological development with potentially profound implications for our lives.
it's kind of a reminder that we should never underestimate the power of curiosity
Absolutely.
and the pursuit of knowledge,
Curiosity is key.
even when it seems like we're dealing with something so abstract
Yeah,
as dark matter.
it's true.
Well, I think this has been a really great deep dive into the mysteries of dark matter.
Yeah, it's been fun.
And I hope everyone listening is leaving with a sense of wonder
Me too.
and, a thirst for more exploration.
Absolutely.
We've uncovered some truly mind-boggling facts about this invisible force that shapes the universe.
We have.
And who knows what incredible discoveries are just around the corner.
You know, it's really exciting to think about.
Yeah, it is. And you know what else is exciting? The fact that anybody can join this journey of discovery.
That's true.
You don't have to be a scientist to appreciate the wonders of the universe
Right.
and the thrill of exploring the unknown.
Exactly.
There are so many resources out there.
Yeah, like books and articles.
Yeah, books, articles, videos.
Videos, even citizen science projects.
Yeah, exactly.
That allow you to, like, really dive deep into the world of dark matter and contribute to our understanding of this incredible phenomenon.
That's a really good point.
Yeah.
All right, well, for everyone listening, keep those minds curious.
Yes.
And those imaginations firing.
Keep asking questions.
Yeah, and until next time.
Yeah, until next time.
Keep on exploring.
See you later.